Okay, hello everyone. So we're going to continue our discussion about ensemble methods and trees today. So just to quickly review a little bit about trees. So a decision tree, what it does is it essentially partitions, it makes a decision about an input based on one feature at a time. So in this example, it looks at the first feature, x1, and it says if that feature is less than t1, we go down this branch of the tree. Then, next step, it looks at feature x2. If that's less than or equal to this threshold, it goes down this branch of the tree, and so on. So that's how the tree operates. That's how it would perform inference, or how it would handle a test sample. Now, the way that we train it is we have to decide exactly which feature we use for this first splitting. Then we have to decide also its threshold. Then if we go this way, we have to decide, well, then which feature should we use for the next thresholding, and what is its threshold, and so on. And eventually we have to decide when we're going to stop and not do any further splitting. So in order to do that, this is essentially how we train the tree. At this stage, so prior to here, we have the full training set. No splitting has happened. And then we consider different features and different thresholds. We essentially consider all the features one at a time and all the different thresholds. And we look to see how we can make the training samples that end up here as similar as possible, while also making the training samples that end up here as simple as possible. So we talked about these homogeneity metrics, and if we're doing classification, we measure similarity in a different way than if we're doing regression, and we have different choices for how we do that. But essentially that's how we train the tree, is we look for a splitting that tries to make these two subsets, training subsets, as similar as possible in terms of their labels. And then for this subset, we do a further splitting into these subsets, and again try to make those two as similar, try to make the samples within here as similar as possible, and samples within here as similar as possible. And there's various ways we can decide to stop. We can say stop once the subset is any smaller than 100 samples. We could also say, in all cases, stop after 3 levels of decisions. Or, as we'll see today, we can also stop based on looking at a cost function. In fact, we saw that, we even saw that yesterday. If we train with a generic loss, and if you notice that the loss before the split is somehow, possibly the loss before the split is going to be smaller than the loss after the split, then you'd say, okay, I shouldn't do that split because I've actually made my loss go up. So I will stop splitting at that branch of the tree. I'll go back to some other branch that I haven't decided yet how to further split that. Okay, so that's basically brief summary about trees. Any questions about trees? Okay, and then we reviewed some of the advantages. So the trees are very general. We didn't really make many assumptions on the data. We can work with features that are categorical or ordinal. We don't even need to standardize the features. We can understand exactly how the tree is making decisions because it's just literally a sequence of very simple decisions it's making. It has fast prediction. This is basically you can say that for a training set size of n, you should have roughly log 2 n levels, and that's how many decisions you need to make. And so that grows quite slowly with n, which is nice. On the other hand, the disadvantages of trees is that when you train them, if at every split you consider all the features, that can be a very time-taking process. And so one solution, we'll talk about more today, is consider only a few randomly chosen features at every split. Another issue with trees is, especially if you consider every feature at every split, they're prone to overfitting. Basically, with enough levels, you can perfectly categorize your training, right? You can essentially process your training so that there's only one sample in every leaf. At that point, you have a perfect prediction of your training, right? But that's not that useful because if you put a test sample in, the test accuracy may not be the same as the training accuracy. So it's prone to overfitting. And to deal with overfitting, we can do things like enforce minimum number of samples per subset, constrain the max depth, and so on. So what we're going to do today is we're going to combine the ideas of trees and ensembles together, and that's when we see when we get really powerful methods. So the first idea, which actually is just described on this slide alone, but it's an important idea, is known as random forests. So the idea is a random forest is an ensemble or a collection of trees. And again, when we make an ensemble, the key thing we have to do is make sure that the different predictors are diverse enough. They're acting differently enough that when we combine their outputs, we see a gain. Right? If the predictors are all essentially the same, you don't get anything from combining their outputs. So in order to make these trees sufficiently different from one another, we can use a random subset of data to train each tree. And in doing that, you could use bagging or pasting. In other words, you could sample with replacement or without replacement. Second, we can use a different random subset of features at every split in every tree. And so that is one of the things we talked about here. Consider only a few random features at every split. So that's a nice way to make the training very fast, but it's also a nice way to make these different trees very diverse. So essentially what you do is you train each of these trees independently, with a random subset of data and forcing a random subset of features to be considered at every split. And this is just a visual illustration, but you can see this is a 2-sample classification data set. I think this is called the 2 moons data set. You have one class that's like this, one class that's like this. You can see that it's not the sort of problem where a linear classifier can do well, because we can't really split it perfectly with a linear boundary. Anyway, if we train that first tree, we get something that looks a little bit strange. The different regions are somewhat disconnected. And this has to do with the fact that we used, we constrained which features we could use at every split of the tree. In this case, there's only 2 features, so if we're going to constrain them, we're only going to use one. We're just going to randomly choose, am I going to use the first or the second feature at every split? And then, of course, we're also using a random subset of the data so that each tree doesn't get to see the full data. In any case, when you look at the individual trees, you can see that they're doing things that kind of make sense, but clearly they're not working perfectly. On the other hand, when you basically average the predictions of those 5 trees, you get something like this, and you can see that that has a much more reasonable decision regions. Like they're things that it's closer to what you would expect. Okay, so this is just an example, but overall, this method is super powerful. It works super well. I didn't write here. There's going to be, for sklearn, they will have made some default choices of how many trees you use. Typically, I'd say you're going to use like in the hundreds of trees. And also, they're going to make decisions about the maximum depth of trees. Like the trees, won't be allowed to be perfectly deep, so they'll have to make an assumption about that. So they'll make various assumptions, and the assumptions they make work pretty well. So if you just run one of these random forest classifier regressors, you'll see just out of the box it gives really good predictions. Now you can improve it. There's all sorts of little tweaks you can make to the hyperparameters, and so if you take on these tree methods for your final project, I would say that random forests are one of the 2 really solid methods to work with. But then your work for the final project would be to go into depth and try to understand how you can improve the performance of the tree by adjusting all these different hyperparameters about how many trees and what depth, and there's all these other things under the hood I'm not going to get into, although I do give some links to articles at the end of these slides of how you can tune these parameters in practice, because there's a lot of tricks, and yeah, there's a bunch of tricks, but you know, there are things that it makes sense if you think about and understand what's happening with all these trees in this forest and so on. Okay, so that's really all I have to say about random forest. It's a great method. We'll see which method wins on the project data set. I actually don't know. This is definitely a contender to outperform everything else. We'll talk about another method next called XGBoost, which is also a really powerful contender, but it's designed in a completely different way. Before we move on, are there any questions about random forests? Okay, making sense? All right. Okay, so the next thing I talk about is what they call boosting. And boosting is the sequential version. Previously, we have talked about methods that work in parallel. So like in this picture, all these trees can be trained in parallel. And at inference time, you can put a test sample through them in parallel. And then you would just combine all the outputs, right? So everything is parallel. But there's another way of doing things, which is serial or sequential. And there's a bunch of methods that do this, but more or less, they go like this. You start with your data set. You train the first model, and typically these are going to be trees. Trees are flexible and fast and powerful and so on. But you could actually try this with other things like neural networks too. But anyway, so you train your model, and then you look at the results on the training set, and you'll notice, you know, maybe you made some mistakes on your training labels. And then what you'll do is you will, there's different variations on this, but basically what you can do is you can change the loss function the next time you train to put more weight on the places where you made an error. And so this next tree is going to be sort of trying harder where the first one didn't do so well. And that might mean that it might, you know, do great on the error samples, but then maybe it does worse on some other samples. Anyway, you know, however this model does, you test it and you notice, okay, that has these new errors, and that is going to determine how you build your loss for the next model and so on. And so you end up training these sequentially, one at a time, but you do in the end combine them usually in an additive way. You scale this tree by a constant, and you add this scale tree and this scale tree and so on, and that's how you get your final prediction. But at least the training is done sequentially. Yes?
Does this all use one data set, or are you using the full data test?
So here you would be using the full data set. Yes. At least in the method as I've seen. Yeah. Yes.
Are the second set of errors are they the errors from the ensemble of those two models, or just the second one?
So are these errors? I guess we'll see how it's done. It could depend on the method. Yeah, but that's right. You could essentially have like these doing the prediction instead of just this one doing the prediction. I think that's what you're saying, is like you could already combine these. Yeah, and I think we might see that for some of the methods, but really there's many different ways you can do this. There's 3 pretty famous ways that we're going to discuss, but there's definitely more than that. Okay, all right, great questions. Are there any other questions? Okay, so let's start with the simplest one and the oldest one, AdaBoost. AdaBoost, as we'll see, we have to make some assumptions, and those assumptions make it tractable, but they're kind of limiting. So what we're going to design is an ensemble of predictors. So we can call these the base predictors. These little f's are essentially these models here. And M will denote the variable indexing through the stages. So this will be M equals 1, M equals 2, M equals 3, and so on. So this is, we want to design that sequence of, or ensemble of predictors. And essentially this is what we're going to do. We're going to train, so we're going to go through a for loop for each stage M, train the predictor little fm to minimize some weighted loss. Now when you look at the weights, this is just, some loss function we'll have to specify. The loss function, as you would expect, takes in the training sample and the output of the predictor. And then here are the weights, and you can see that the weights depend both on the stage as well as the training index I. Right? So every training index has a different weight, and the weights change with the stages. And the intuition is that based on what happens in the mth round, you look at the errors and you assign larger weights to the samples in the next round. So that here we have Wm plus 1. So that's what I was explaining here is you can, if you made an error on one sample at one stage, then the next time you somehow treat it more seriously. You say, I don't want to make that error again. So this is how you design these predictors, the little f's, base predictors. And then the final prediction is done using a weighted average. So here are base predictors, and then here are weights that we have to design for the different stages. Okay, so that's essentially how we'll do it. We'll go through the steps, the details on the next slide. Any questions at the high level? Okay. Okay, so now for simplicity, we're going to focus on models. First of all, classification. Second of all, binary classification. And more than that, we're going to focus on these predictors that give either 1 or -1. So they give hard outputs, right? Not soft. And this is going to make our derivation easier. There definitely are other versions of this. There's versions for regression, for non-binary classification, maybe for soft output classification, I'm not sure. But we're just going to go through with this simpler case just to get a feel for how this procedure goes. Okay, all right. So as usual, this is our training data set, XY pairs. We're going to assume that our training labels are binary plus -1. The base classifiers, as we said, they output plus -1. And essentially, this is how we train them. So let's first of all define this step M boosted classifier. That's going to be capital F. And you can see we're taking the previous boosted classifier and we're adding on a scaled version of the base classifier to get FM. Okay? And so we're going to initialize the boosted classifier at stage 0 just to be 0. So, this is gone for the first stage. First stage, you just have a base classifier. And we want to design both the alphas and these Fs. And the Fs are going to be, trees in practice. Okay, and then this is essentially how we do it. We have a for loop over little m. We design a positive alpha and an F so that the boosted classifier minimizes an exponential loss. Okay, so to answer the question from the first row, so in this case, you can see that we are in fact using the boosted classifier that we have at that time. So we're using sort of the weighted sum of all the base classifiers up till that point. Okay, and then we're choosing this exponential loss basically for tractability. Exponentials are nice because they're easy to differentiate and so on. It is a little bit of a weird loss otherwise because just to give you some perspective, we've seen a couple other losses for classification. We have seen hinge loss, which looked like this. We saw logistic loss, which looked kind of like this. In both these cases, the slopes down here were linear. Exponential loss does something where there's an exponential here. So basically, it really freaks out when things are wrong. So I would say it's probably not the most robust loss, but it is what is used, at least for this derivation. You don't see it very often in machine learning, but just once in a while when you're looking for a loss that makes things trackable. So anyway, that's the method. And so now we can plug these ingredients in to see how we would perform the optimization. So, okay, so we have, so this is the loss at stage M. We're going to take this expression and we're going to plug in, for capital FM, we're going to plug in this expression here, and that gives us this. Okay, next, we can write this e to the power, that's a sum of two things, as e to the first times e to the second. And we can notice that this first exponential are things that we know completely. Obviously, we know the training, and when we design, here our goal is at the nth step. We've already designed fm minus 1, so we know that. So basically, we can just evaluate these numbers, and we'll rename them something simpler. These are our weights. You could say the weight on the ith sample for the nth model, and these are just numbers we can compute. Okay, so this part now contains the things that we need to optimize over, which is the alpha and the f. Okay, so the next stage of the derivation says, sort of does a little trick. It says, let's break this sum over all the training samples into two sums. The first is going to be the sum over all the training samples where we made a correct prediction on the training data, and then the separate sum here over all samples where we were incorrect. And since it's binary, there's either we were correct or incorrect. Now, if we're correct, then that means that yi times fm xi, they're either both positive or both negative, so their product is 1, right? And so at that point, what remains is e to the minus alpha m. That doesn't actually depend on the index I anymore, so you can actually bring it out in front of the sum. And what remains is actually, in that case, just these weights. On the other hand, if you had made an error, then yi times fmxi is going to be -1 in both cases. And so that negative will cancel this negative, and you'll have e to the alpha m, which again comes out in front of the sum. So hopefully, does everybody agree with me on this step? Okay. Now the next thing is we're gonna complete this sum. We're gonna add in all the samples I that are left out. In particular, we are going to add exactly this to this sum. And if we add all those missing samples, then the sum will be complete. It will go from I to n. Okay, so if I add that stuff to this sum, I must also subtract it to get an inequality. So here is where we're subtracting that stuff. Okay. As a result of this, the reason we did this is we were able to now squeeze f into just this term, because we want to optimize over f. So here the optimization is difficult because f was present in both terms. Now we managed to squeeze all the f into this term, and for the optimization of f, we don't have to consider that at all, right? In fact, for the optimization of f, we don't even have to consider this, because for that stage m, this is just a fixed constant. So to optimize f, all we have to do is maximize this. Sorry, minimize this. Okay, is everybody okay with that? Okay, and what are we minimizing exactly? If you think about this thing we're minimizing. So number one, we're penalizing only the samples where we made errors. Those are the only samples in the sum. And second of all, we're penalizing those samples by weights that had to do with how well we did in the previous stage. Okay, so basically, this is some weighted misclassification loss where the weights were computed based on how well we predicted in the previous stage. If this is a confusing way of writing it with this complicated sum, you could also write it like this, where now the sum contains all the samples, and this is an indicator function that takes on the value 1 whenever this is true, and otherwise takes on the value 0, which would mean that it removes, all the terms in the sum here for which we did not make a mistake. So just a different way of writing it. So that's essentially how we design this classifier. So at the very first step, we would set all the weights to 1. So we just want to minimize classification error, and we can do that. We saw Monday, we saw a way we're given a generic loss and a top-down tree design. We saw a way that you can just split at every layer to minimize that loss, and so that's exactly the procedure you would follow here to train really any of these predictors. The first one at stage m equals 1 just uses weights that are all identical, but at the future stages, the weights are determined, they're large if the previous boosted classifier made a wrong decision. So that's just, that's from here. Okay, so that's essentially how we can go through and design the classifier at every stage. Now, the other thing we have to design are these scalar weights alpha m, but that actually is pretty straightforward. We can just take the derivative with respect to alpha m, set it to 0, and solve for alpha m, just like we've been doing all semester. And I don't have the details here, but if you did that, you get this nice expression where alpha m takes on this form, where these epsilon m's you can think of as a weighted error rate. So here, this is the sum of the weights over the places where you made errors, and this is a sum over all the weights, where you made errors and where you did not. So you can interpret this as a weighted error rate, and then alpha m is just a function of that error rate. Okay, so basically those are all the steps. Just to understand them all together, what you would do is you would initialize all these weights at 1 for the first stage, little m equals 1, and then for the previous stages, for the following stages, you would first compute this tree. Then you would, once you know the tree, you can compute this because you know the weights, you initialize them, you know f, you know the training data, so now you can get these epsilons. From the epsilons, you can get the alphas. From the alphas and the f's, you can build your next capital F, and from your next capital F, you could compute the weights for the next iteration, and then just repeat. You do this for each m. And eventually you get all of your base predictors, all of your alphas, and then your final model, your final boosted model is this capital F, capital M. Okay, so that's how AdaBoost works. I don't know if this is confusing. There's definitely a lot of different steps, but can I answer any questions on this? Okay, no questions? Is it just sort of too much? Too much information? Okay, I apologize for that, but okay, so here's a little illustration, visual illustration of how this might happen. It's a binary data set with two features, x1 and x2. Maybe at iteration 1, okay, so your data, as you can see, you have these blue crosses and red minuses. So at that first iteration, we're going to essentially, let's say we design a decision stump. So a decision stump is a tree with one level. That's it. So a decision stump would basically split your feature space in half. And one decision on one half, the other decision on the other half. It's simple as that. So in this case, we're making the split this way into these two regions. And as a result of that, you can see that here in this blue region, we classified correctly all the blue pluses. But in this other region, these minuses were correctly classified, but these were in error. So now that we made a mistake on the blue pluses here, for the next time we would weight them more. And you can see that reflected by how the font size increased. So now we're saying, this is our new training data, but these pluses count more than all the other samples. because they have a higher weight. And now for this new training data set, we again, have to make a decision stump. So we make one more, we have to split this somehow into two regions. And so we decide to split this way. And that means that now these samples are going to be misclassified. Everything else is perfectly classified. So the next time, these guys get a higher weight, and so on. And when we're done, each of our base classifiers as a stump is pretty limited. But when here are alphas, they were optimized with setting the gradient to 0. When we combine 0.38 times the first one plus 0.58 times the second plus 0.87 times the third, we finally get a final classifier that, as you can see, perfectly classifies all our training data. So even though these base classifiers are weak learners, they were really simple. By putting them together, we got a really strong classifier in the end. Okay, so just a visual toy example. In terms of the scikit-learn implementations, so the AdaBoost classifier uses 50 decision tree classifiers with depth 1, stumps. And the AdaBoost regressor uses 50 decision tree regressors of depth 3. So those are the choices that they made for sklearn for the defaults, but of course you can change them if you like. Okay, so that's AdaBoost. Are there any questions on anything? Okay, so let's move on to gradient boosting. So gradient boosting, you could say it tries to be more general. In searching for that generality, it has to make some approximations. So we'll see how that goes. So basically, this is our loss. Our overall loss looks like this. You can see that we have overall, there's a script L, and we're summing over our training samples, and our per sample loss is this non-script L. And this is what we've seen before. This is just some loss that compares the true label to the output of the nth stage of a boosted tree. So this is, this is like the final stage of this boosted classifier that we designed. As before, the nth stage boosted classifier is a sum of these base learners, each multiplied by alpha m. But now, or I guess before too is the case, so these base learners should be in some family of models. So for example, a tree, decision tree. So that's what this script F means. This is a model class. It could also be a neural network. It could be a linear classifier, linear regressor, whatever it is, like you decide, but at the end of the day, we'll see why it's important to name this and remember that this really has to be part of some class. Okay, so we saw an example of this with AdaBoost. And in particular, what AdaBoost did is it could handle this with exponential loss and with binary tree classifiers that output plus minus 1. So that's like, tree classifiers outputting plus minus 1 is one example of this script F. Okay, so our goal now is to generalize this. Can we do this with more than this exponential loss and with more than just binary tree classifiers? That's the goal. So ideally, this is what we would like to do. So take the sequential approach. First, at stage 1, we train our base classifier little f1 to minimize this. We saw how to do this on Monday. For a generic loss, we know how to do this at least with a tree. And once we design that first base classifier, we'll just set the capital F1 equal to that little f1. And then over subsequent stages, we will try to add to this. We will say the next boosted classifier is the previous plus alpha FM, just like this. But we want that the alpha and FM that we use are the ones that jointly minimize the loss of the resulting classifier. So this is the previous boosted classifier. This is the alpha M and FM that we are trying to design. We want these two together to work as well as possible on that loss, right? So this is the optimization says, if I combine alpha and F with my previous capital F, then those are the best ones, and those are the ones I'm going to use in this combining. Okay, so hopefully that notation is clear. The problem is that this optimization is just too difficult for most losses. We saw how we could do it with exponential loss and binary outputs, but in general, it's just not tractable. So the whole idea behind gradient boosting is to approximate this exact optimization with a gradient step. Okay. In other words, instead of doing this, we're going to do this. So we're going to say that the new boosted classifier is the previous one minus some scaling alpha m of the gradient. So this is a familiar idea, right? We've seen this with gradient descent and so on. So here we're using it in a slightly different way. But, I guess the hope is that we're taking steps in the right direction. We're taking a bunch of little steps in the right direction. Eventually, we will get this F capital M will be good. And so this is, so the hope now is that maybe we can't do this optimization exactly, but we could at least take the gradient. That might be tractable, and maybe we can do this. So that's sort of the high-level idea. Is this making sense? Or can I clarify anything? Okay, so we want to essentially do this, but there's a catch. There's a big problem. So remember that what we really need to do is we need to say the mth state boosted classifier is the previous boosted classifier plus alpha m times fm, where fm is some model that we know how to design. For example, like a tree. So the problem now is when you compare this to this, if they're going to agree, that means that this gradient needs to be implemented as a tree, right? Or if you're working with neural nets, it means that this gradient needs to be implemented as a neural net. Or if you're working with linear classifiers, it needs to be implemented, right? But this is kind of like, who knows what that's going to look like? You have some function capital F, which could be complicated. Now you're taking a gradient. This is an even more complicated function. How are you going to actually implement that? It just might not be possible to figure out how to design a tree to actually do this. So that's the big catch now. Gradient descent does not constrain this update to the set of base predictors. So here we have to make a second approximation, and this is the second of the two main approximations for gradient boosting. Okay, so we are going to train F to be close to the gradient, but still within the model class. So maybe we know we're going to be using a tree of a certain depth. We're going to try to optimize that tree so that its outputs are as close as possible to that minus gradient of this thing that we ideally would like to use here. Okay, so how do we do that? Well, let's take a look at this gradient. So the gradient that we're talking about, we have our loss L, that was the per sample loss. We're evaluating this at the previous boosted classifier FM. Depending on the form of that loss, we should be able to take a gradient with respect to a derivative with respect to the second argument. And then we're going to get some function, but we can certainly evaluate that at all our training samples. So what we're going to do here is we're going to get a set of numbers, RMI. M is just fixed for the stage, and I spans over our training set. So essentially, we would like to train our model F to generate outputs that are close to these numbers. These numbers become kind of like the training labels for our model now. And we're just going to use quadratic loss. So here are our targets, these guys. Here is our model that maybe is the form of a tree, or whatever. We're just going to train that tree to minimize this quadratic loss. We'll get some design, and then the next thing we have to do is we have to choose alpha. So now FM is fixed. We designed it. This is a pretty simple problem over a scalar parameter. If we can't solve it analytically, you can just make a grid of different alphas and see what happens and choose the best one. It sort of depends on the loss and so on, but it shouldn't be a big deal to solve this problem, just optimizing a scalar parameter. And then we're done. We have our base model, we have our scalar, we add it to our previous boosted model to get our next boosted model. Okay. So the two main ideas here were, instead of doing this exact optimization, you settle for a gradient step. And then instead of doing the exact gradient step, you do an approximate gradient step within your model class. Okay, so that is gradient boosting, basically. All right. Again, a lot of information, so I don't know if it was too much, if it made sense. Are there any questions on anything here? Yes.
You're saying this like lets us mix and match the different approaches? Like,
So, yeah, so it's kind of, you could say, inspired by AdaBoost, but now we can use an arbitrary loss. It could be quadratic, it could be logistic, it could be whatever you want. And using this gradient approximation and this other stuff, you can handle it. So it's just totally general. Okay, all right, any other questions? All right, so just a few implementation details then. In practice, it helps to slow down the updates. So even after you do this optimization of alpha and F, typically you put in some mu that's between 0 and 1. I think you can read theory about why this helps and so on. It helps for generalization, but in any case, when you go to the sklearn implementations for classifiers or regressors, you see that they use mu as 0.1 in both cases, just as a data point. And for classifiers, they use 100 decision trees of depth 3. Same thing for regression too. So just to give you a flavor of what sklearn does to implement this. Okay, and here's just one visual example. This is prediction for a single scalar parameter regression. So here's our scalar feature x. This is our target y. The true model that we're trying to approximate is this blue line. So we're trying to design, a gradient boosting model to approximate this blue line. Let's look at what happens if you use a regression tree of max depth 1. So if I have a regression tree with only depth 1, how many different outputs can it give? Two, right? You split it, so you're going to give out one output or the other output. So here's a picture. This green line shows just an example of, this is an approximation of that blue curve with a single regression tree of max depth 1. Obviously, terrible approximation, right? What if I do it with the regression tree of max depth 3? So now, if I have 3 splits, how many outputs can I get? So think of a tree branching. How many leaves do you have after 3 splits? 8, right? 2 to the power 3. So there's 8 possible outputs. So I don't like the fact that they used green again for this, but there's another line here. And you can verify this has 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's just an example of how close you can get to the blue line with 8, a single regression tree of max depth 3. So what we're going to do here, though, I'm not exactly sure if they used 100 like sklearn does, but the red lines show gradient boosted regression tree, and essentially it shows the sequence. So like the first stage in the gradient boosted regression tree is using, I don't know, maybe they even use stumps. I'm not exactly sure what they use here, but basically it's maybe a really simple model. And then the next time it gets more sophisticated, and it gets more and more sophisticated. And finally, after, looks like they used 2,000 different, maybe 2,000 stumps, they finally get to this classifier, which is the red line there. And here they're illustrating the fact that when you start out with this, very simple model, you have something that's high bias, it's very far away from the truth, but it has low variance, probably. It's very stable over different realizations. As you have more and more layers, you reduce your bias and increase your variance, or more and more stages. So again, just a visual example of a gradient boosting regression. Okay, so we're getting to the end now. The last thing to talk about is an evolution of gradient boosting called extreme gradient boosting, or XGBoost. And XGBoost is really one of the favorite models for machine learning contests. It works really well out of the box. It's just sort of like the standard first step to do in any machine learning contest. You just run XGBoost, and maybe if you tweak XGBoost enough, you'll win. It's just often, with the right amount of tweaking and everything, XGBoost is the winner. Okay, so XGBoost is very related to what we did with gradient boosting. It just adds a few tweaks. Instead of doing just a single derivative, like we saw with gradient boosting, it does a second order Taylor series expansion. So it's looking at slope and curvature. It adds regularization. It has a sophisticated tree search and various parallelization and hardware acceleration tricks. So we will not focus on the second details. We'll just focus on those first two steps. And the XGBoost package is not part of sklearn. It's like a standalone package with some, I don't know if it's an organization or who maintains it. However, they wrote it in a way that there's different interfaces, and one of the interfaces is exactly like scikit-learn. So you can import it, and you can use it as if it was scikit-learn, and it just works perfectly within the scikit-learn environment. Okay, so let's go through the derivation. So in this case, the boosted predictor does not have the alphas, the alpha m, so it's a little bit simpler. You're just going to sum together the base predictors to get the boosted predictor. Okay, so ideally, this is what we would like to do. First step, we train the first base model to minimize this loss. And then for all the other stages, we train the base model to again minimize the loss, and then we add it to the previous boosted model to get the next boosted model. So here it's identical to gradient boosting, except there's no alpha m's, but there is something new. There is a regularization term. Okay, we'll get into the details of this, but that's the other piece of the puzzle. So they took out the alphas and they added this. And just as what we saw before, when you try to do this optimization exactly, it's too complicated. It's something you can't really do in closed form. So instead of using a gradient approximation, we're going to use a second order Taylor series approximation now. Okay. And we're going to do the approximation. So this is the term we want to approximate. And we're going to do Taylor series about this term. So we're going to think of this as the perturbation. Okay, so here's that term. The second order Taylor series says you have the 0th order term where you just set this to 0. Then the first order term says you look at the gradient of this with respect to the second argument. We'll call that GMI. And so you have GMI times the perturbation. And then the third term in the Taylor series says you look at the second derivative of this with respect to this term. We'll call that HMI. And then you multiply that by the perturbation squared. Okay, so this is just a standard second order Taylor series. And now our objective here is to minimize this, to optimize over FM. So the first thing you notice is that little fm is not even part of this first term, so we can just forget about it for now. We can just focus on optimizing this plus the regularization. Okay, so that gives us, this is essentially our cost function. We want to optimize this over fm. So we see fm appears here in the square, and it appears inside the regularization. Okay, so is everybody with me so far? Again, I know a lot of stuff here. Okay, so that's our objective. Now a few details about how we're going to do this optimization. So we're going to use the same trick that we used back on page 15, where for fm, or let's say for this predictor as a function of x, we're going to write it sort of as a two-stage thing. We're going to write it as z with subscript q of x. So zl is the output the tree assigns to leaf L, right? This is just sort of the values in our lookup table. And then Q is the more complicated thing. This is the function that takes in your feature vector x and tells you which leaf it ends up at. So this is the part that really has sort of the tree structure. Okay, so f of x we're going to write as z sub qx. Qx is the tree part, zl is just the scalar output in our lookup table. Okay, so that's one thing to note. We're going to use that to solve this. The second thing is, okay, what about this regularization? So the regularization has this form. So the first term regularizes to penalize the sum squared outputs. So it's reminiscent of ridge, but it's a little different because in ridge regression we were penalizing parameters, like slopes. Now we're actually penalizing the outputs directly. Okay, but it is what it is. So lambda is some adjustable weight that we can place on this first term. The second term in our regularization is going to somehow penalize L. L are the number of leaves in the tree. So we'll see, it's not obvious now, but we'll see that this second term will actually help us not go too deep in when we do our trees. Okay, so that's essentially the regularization that XGBoost uses. These are some numbers we'll need to tune. These are things that, they come up with default parameters, but these are the sort of things you can tweak a bit to maybe get it to work better. Okay, so let's come back to our optimization problem here. To make things a little bit more compact, we're going to omit the M notation. M is just the stage we're working at, so M is constant now, so let's just not get distracted by M. So essentially, I'm just rewriting this equation without the M's so that, let's see, I can't view it all at the same time. Oh, yeah, here we go. Okay, so this part is this, and then this part is this, the regularization. Okay, now, when writing this sum over I did this trick, the same trick did last time in a similar place, where we're going to write this as a two-stage sum. First, we're going to sum over the leaves in our tree, and second, we're going to sum over the samples I that end up in a particular leaf L. So sum over leaves, sum over samples for a given leaf. And what that allows us to do is, so like this term, fmxi, I can just write this directly as ZL, because here I'm saying sample I will end up in leaf L, so if I know that, I can just write this in terms of ZL. In terms of this term, it's the same thing. I just have h times f squared, or h times ZL squared. And then for the last regularization term, that was written like this originally, just directly in terms of the ZLs. Okay, so this is the optimization problem we want to solve. We want to solve this, we want to design the tree and the Z jointly to minimize this new loss. Okay, so how are we going to do this? First step, let's rearrange things. Let's collect all the terms that are linear in the outputs. So actually there's just one of them. But let's sum this. Let's think of this. Just trying to be clear here. So there's a sum over I that affects the GIs. So I put parentheses around there, and then we have ZL. So that's just the first term. Then we have two different terms with ZL squares. So I'm collecting both of those here. So the first one, we have a sum over L times lambda. So here's our sum over L times lambda. And then the second one, we have a sum over L times essentially 1/2 HI. Oh, and we have the sum over I. So that's this part. And then the very last term, we have a lambda here, but because I'm putting that inside the sum, that will add up L times to make this L. Okay, so finally, we get this cost, which is sum over leaves, and then for each leaf, we have this particular cost. Okay, so just one more. We're almost done. Okay, so if I want to do this optimization, what I can first do is I can fix Q and optimize over Z. So optimizing over Z is easy because it's just a quadratic in Z. So I can take the derivative with respect to Z, set the result equal to 0. And when you do this, you find that the Z's have this form. So if you know your Q function, which we'll design next, and these G's and H's, you can just compute the Z's in closed form. Okay, so now that we know the form of Z, we can actually plug this back into this equation, and it simplifies drastically. There's one, I noticed that I did one little, let me just clarify a little bit. So for some reason I multiplied it by 2. Let me take out that. So if I have the gamma here without the 2, and if I have a 1/2 here, then that's exactly what you get when you plug Z in here. So to see why this occurs, so number one, we have the gamma arising here. Okay, if I plug this into here, I get the numerator appears squared and the denominator appears as it is. Now, if I plug this into here, then because of the squared here, the numerator appears squared, the denominator is squared, but I'm multiplying by the denominator here, so I just have the denominator as a single power. That means that both of these terms have exactly the same form. The only difference is one of them has a multiplication by 1/2, and so as a result, this thing simplifies down to here. This is the problem we have to solve, minimizing over Q. And this is basically a tree design problem for this very particular loss function here. And we described how we can do that back on page 15, how we can design a tree for a generic loss. So you just plug in this loss, you design your tree, and essentially that's the procedure. Now, there is something sort of interesting to note. Let me make this little correction. So I'm going to get rid of the 2, put a 1/2 there. Okay. So one interesting thing to note is when you're doing that tree design, you keep splitting your data into 2 parts, and you evaluate the loss before the split and the loss after the split. When you look at the loss after the split, you can see that the value of whatever you assign for gamma actually doubles. So here before the split, gamma counts once. Now after the split, gamma counts twice. And so essentially, this is where you decide whether you want to actually do the split or not do the split. Because if the loss has increased, then it says don't do the split. I actually made things worse. And you can see that the reason the loss might increase is because gamma has doubled, but perhaps these other terms, which are negative, do not counteract, they don't shrink enough to compensate for the doubling in gamma. And so the larger gamma is, the more likely that is to happen, and the more likely you are to terminate your tree. And you can see now, when you look back at how gamma first appeared, this gamma is essentially regulating the depth of the tree. The larger the gamma is, the shallower your tree will become. essentially. That's what's happening. That's how gamma is working. Okay, so if you want to see more details, the original paper has a bunch more, but those are, I think, the things that are important that I wanted to get across. Let me just very quickly finish up. I think we just have essentially one more slide. So all I want to point out is, in terms of the implementation, you have to grab it from a different package, but after you do that, it's identical to how you would treat it as if it was an sklearn model. You instantiate the classifier, you do model.fit, you do model.predict, and that's it. And it even plays well inside other scikit-learn commands that accept predictors. So that's also pretty cool. There is a demo. I didn't import any of the pictures of the demo into these slides, but I do have a demo up that if you actually want to see code, it contains random forest and XGBoost. And the other thing the demo does is it shows how these tree methods have built-in ways to do feature selection. So when you design the tree, you can see how the data flows through the tree, and you can notice that certain features might do better in terms of making things pure. So remember, when we go through the tree, we split according to one feature, another feature, and so on. So if you look at all the times you split according to, let's say, the first feature, you can see on average how well did it do to purify the data into these two buckets. And so maybe you notice that this first feature is working way more efficiently in terms of organizing the data than the second feature. Then you might say, well, that first feature is more important. So it gives you a sense of feature importance, or what we use for feature selection. So so there's a bit of caution, like the results you get from these tree models, there's different ways they can measure feature importance. And they work pretty well, but they're not perfect. And so there's an experiment in the demo where I generate two completely random features. One is Gaussian and one is discrete. And I show that the tree models actually, they think that these features are a lot more important than they should be, right? If these are random features, they should be less important than anything else because they have absolutely nothing to do with the targets. But mistakenly, some of these tree models actually give some of those features pretty good importance. And so that's sort of a warning sign. And there's many other articles on the net about being careful with feature importances from random trees. I mean, they're not terrible, but they're not perfect either. And then I showed in the demo, there's another scikit-learn method to do feature selection called permutation importance. We never discussed it back in Unit 4, but it's a pretty robust method. And you can do it on these trees, and at least in the demo, it works perfectly. But if you repeat the demo under different random seeds, you'll see it's not always perfect. So there's basically no perfect method for feature selection, except for the brute force one we discussed way back when. But usually that's in most cases, that's probably going to be too expensive. So feature selection is an important thing, but it's also something that in practice, it's a little bit more of an art than a science. You can try different methods, see what works best. So that's all I have to say about Boosting trees. There's this last page that has links to see how to tune random forests and XGBoost and so on. And these would be useful if you're doing the project on the tree methods. I would say dig into these articles and read about the tricks and then try what they suggest. Okay, so that's it. Sorry for going over time today. If you have any questions, just come up and ask me now. I'll see you guys on Friday.